Tonight, we will hear the 12th annual Tansley Lecture presentation. And this annual event is called the Tansley Lecture to honor the late Donald D. Tansley for his remarkable career as a senior public servant in Canada. Donald Tansley, an alumni of the University of Saskatchewan, began his career as a public servant with the Government of Saskatchewan in the Budget Bureau, under the guidance of Al Johnson. Throughout his career, Mr. Tansley was known for leading some of the most complex and contentious files in the provincial government, from rescuing IPSCO from bankruptcy, to implementing Medicare in Saskatchewan, to leading the modernization of the provincial government in New Brunswick, and implementing highly controversial policies such as the Program of Equal Opportunity. In 1968, Mr. Tansley moved to the Federal Public Service, where he served as Vice President of the Canadian International Development Agency, advisor to the Red Cross, and CEO of the controversial Anti-Inflation Board. And finally, he led the development of the Department of Fisheries and Oceans. Whatever the challenge, Dr. Tansley's character and commitment to the public service always shone through. He could often be heard encouraging his colleagues to persevere and finish the task at hand, and to take hard judgment with a grain of salt. I am now pleased to invite Dr. Carrie Finley to the stage to introduce tonight's speaker. Dr. Finley is assistant professor with the Department of Biology here at the University of Regina, and her research focuses on aquatic ecology and biogeochemistry, specifically investigating the role of prairie lakes in the global carbon budget and the effects of anthropogenic activities on lake water quality. Please join me in welcoming Dr. Carrie Finley.
Thanks for that introduction, Alex. And thank you so much to Johnson Choyama for setting this up tonight. Really excited to listen to Jay's talk tonight. And really appreciate all the work that Doug Moen and Karen Jaster and everybody else have done in order to make this a really, really special evening. So I'm really happy to be able to introduce tonight's speaker, Dr. Jay Famglietti. Dr. Famglietti is a professor of hydrology and the executive director of the Global Institute for Water Security at the University of Saskatchewan. And he also holds the Canada 150 Research Chair in Hydrology and Remote Sensing. Before moving to Saskatchewan, Famglietti served as the senior water scientist at NASA's Jet Propulsion Laboratory. His research group uses satellites and develops computer models to investigate how the water cycle and freshwater resources are being impacted by climate change. Through this work, his research group has developed methods to identify groundwater depletion in the world's major aquifers. Given our semi-arid climate in southern Saskatchewan and recent climate projections that are predicting highly variable precipitation in the future, we believe that this research is going to be really, really important for this region in particular, as well as many other regions across the globe. We had the opportunity this morning to meet with Dr. Famglietti at the Faculty of Science, the Institute for Environmental Change and Society, and we had some really great conversations this morning about some of the issues that we are facing with water quantity and quality. We also had some really great conversations about communication and the need for outreach and working with people in policy in order to address these issues in a timely fashion and with solid science behind it. So we're really looking forward to hearing more details about the research that Dr. Famglietti has been doing and how we might be able to apply that in Saskatchewan and hopefully come up with some potential management options in future so that we can address these really crucial issues. Thank you, and welcome, Dr. Famglietti.
We were having a conversation before about like seeing your picture, like who's that old guy on the screen? It's me. So thank you. So I have a mobile mic here, so I'm going to roam around the stage and point to some of my slides and hopefully be able to explain them a little better to you. Thanks. First of all, thank you everyone for coming. It's a pretty big crowd. So thank you. Really, really appreciate it. Great job, students, on those posters. Awesome. And Doug and Karen, thanks for organizing such a great event. And I really enjoyed meeting with everyone on campus today. So it's a pleasure and honor to be here for the Tansley lecture. I really, really appreciate it. And one of the first things I did when I got to University of Saskatchewan was find Murray Fulton, the director at the USask, Johnson Shioma campus at USask, and showed him some of the work that I was doing. And then Doug came by another time, and I showed him some of the work that I was doing. I'm not a policy person. I don't even play one on TV. But I think that the work that I'll show you today has really, really important implications for some of the policy needs, innovations, and challenges that may be coming down the road as we think about some of the images that I show you and what they mean to you. And I'd be interested to hear your feedback on what they might mean to you from a policy needs perspective. So my talk is called Changing Water Availability as Viewed from Space. Implications for water, food, and human security and emerging policy needs. And those images on the right-hand side, I'll go into those in a little bit more detail, but they are outtakes from animations on the upper part here. That's California. And this is the Middle East, and this is northwestern India. And these are some satellite images that we've been working with, and think about what they mean for water resources and the change in water resources in those areas. And each one of those regions has some important policy implications. Groundwater management in California, human security, and migration from Syria in the upper part of the Middle East, and some of the tensions across the India-Pakistan border and what that might mean for transboundary water sharing, whether it's groundwater or whether it's surface water. Okay, so as an outline, I'll start off by defining what I mean by water security. It's a very simple definition. Then I'll talk about what satellites are telling us about water security, and in particular this satellite mission called GRACE, which I'll explain in a minute, that we've been working with for so long. And then what are some of the implications for and emerging policy needs for water, food, and human security? And the last part, what are we going to do about it? I don't have the answer, but we can talk about it maybe in the Q&A. Okay, so defining water security. I use a pretty simple definition of water security. Can a region provide a reliable supply of potable water to its population, both now and into the future, okay? To do all the things that region wants to do. So reliable supply, that's becoming more challenging as we think about, as Carrie was just talking about, the variations that we're going to start to experience with precipitation. And the increasing frequency of flooding and drought. So providing a reliable supply is going to be a challenging job for water managers in many parts of the world. Potable water, of the appropriate quality for drinking, but these days we're thinking about using lower quality water to do different tasks like household plumbing. So we have some options there. To meet all of the demands of a region, so that's what these pictures refer to. So water for irrigation to grow food, water for the environment, drinking water for people, water for energy production, water for economic growth, okay? And both now and into the future, so thinking about climate change, thinking about population growth, and thinking about how technology might help us out, right, in a positive way to close that gap between supply and demand. Okay, so what are satellites telling us about water security? I want to tell you a little story about, or a little history of a satellite called the Gravity Recovery and Climate Experiment, or GRACE, which was launched in 2002. Sorry, this didn't mean to hit those. So the GRACE mission was launched in 2002, and as I said to some people today, one of the nice things, fortuitous for me in terms of my career, was that the entire mission really fell sort of in the sweet spot of my career. I started hearing about it right when I started as an assistant professor. I was at the University of Texas at the time, where the PI was located, and there was a big team there, and that's really how I got engaged in it. Then the satellite launched in 2002, and there's this time period I had lots of students who got to work on it. And then we get to write a bunch of papers, and the satellite was decommissioned, crashed, and burned in 2017. And now I'm sort of at this point in my career. As you'll see from some of the things that I talk about today, where I really want to do something in response to some of the findings that we've made through the years. Okay, so GRACE. The satellites are not particularly big. They orbit at about 400 kilometers. They are 200 kilometers apart. Or you can see here, they're not particularly big. You know, they're probably about the size, if you put like maybe 3 of these together, they're probably about that size. So it launched in 2002. It was decommissioned in 2017. It was really only supposed to be a 5-year mission, so there's another bit of luck. And it just kept flying and delivering data for 15 years. It functioned like a scale in the sky. And I explained this to some of you this morning, but I'll explain it again, really just because I want to play with these glasses. So the 2 satellites, I showed you that orbital configuration. They're separated by about 200 kilometers, and they're up about 400 kilometers. And they orbit over the poles. So they're going like this, right, around the world. And what happens is they're really responding to the tiny variations in space and time in Earth's gravity field that are caused by the movement of water over the surface of the Earth. Let me explain that in a little bit more detail. So imagine the satellites are flying over the Rocky Mountains in the western United States, and there's just been a snowstorm. Okay? That region has gained water weight. And so as the satellites fly by, they're flying over the Rocky Mountains, and they're over the Rocky Mountains, first one comes in, that region has gained water weight, so it exerts a slightly greater gravitational tug on the satellites and pulls them down just a little bit. Okay, so first one comes in and does this, second one comes in and does this. Okay, so likewise, when the satellites are flying over a place like California, where I lived for so long, that's been losing groundwater, and western U.S. has been in this colossal drought, that region has lost water weight, and it exerts a slightly less of a gravitational tug on the satellites, and they fly just a little bit higher as they're flying over California. Okay, so by keeping track of the ups and downs of the satellites, I guess I can put these down now, we're able to map out the regions of the world that are gaining or losing water mass on monthly and longer timescales, and produce some of these maps that I'll show you in just a couple of slides. So pretty incredible technology. I can't take credit for it, but I would like to, but I can't. It measures the changes in total water storage, not the absolute amount. We can't measure the absolute amount from space. We can only measure the change. And it's the total amount of water, all of the snow, all of the surface water, all of the soil moisture, the moisture in the soils, and all of the groundwater together. If you want to split that apart, we need more information. I'll show you some research that we've done on that. It works at pretty low resolution in space and time, monthly and longer time scales, and 150,000 square kilometers and greater. 150,000 square kilometers. Saskatchewan, I looked, Saskatchewan is about 650,000 square kilometers. Okay, so it's pretty coarse. So it's not a weather satellite, but it's really perfect for giving us this big picture of what's happening around the world. So hopefully, you know, Carrie mentioned I was at NASA for a while, and got to really participate in the development of future satellite missions, which was a lot of fun. And so my colleagues and even my students will be working on thinking about what to do in future missions, where future is probably 10 or 20 years down the road, because satellite missions are quite competitive. That said, we did manage to get what's called the GRACE FollowOn mission launched last May. Okay, so the original GRACE mission ended in 2017, December 2017, when the satellites crashed and, again, literally crashed and burned. The GRACE follow-on mission is what we call a climate continuation mission, which means it's pretty much the same thing. So it's a class of missions. Satellite missions are quite competitive to get funded. And so, you folks at Table 3 might have a mission that you favor, and you put together a team and write proposal, and you folks at Table 4 might have a mission. I like Table 3 because that's where I was sitting. So it's competitive. And so the reason we were able to get the GRACE FollowOn mission funded and launched is because we called it a climate continuation mission. The data that we were collecting on ice sheets melting, and I'll show you that in just a couple of slides, ice sheets melting, sea level rising, and changing water storage on land were compelling enough so that NASA and Congress agreed to fund it as a continuation mission, to keep it going. Okay, so here's what some of the data look like. So we're going to look at the Middle East, and we're looking at an animation here that's going to go from blue, green to red from 2002 to about 2014. And we're looking at really the cumulative water loss in this region. So in a sense, we're making the invisible visible. A lot of what we're looking at is the change in groundwater storage. We've written papers on this area, and we're able to determine that about 60% of what we're looking at here is due to changes in groundwater, so groundwater pumping. And this is what the time series for that region looks like. And so we're looking at 2002 to 2017, the full GRACE time period. And does anyone see that, or am I just going blind? Okay, anyway, every dot there, so we're looking at wet season. The peaks are the wet season, the troughs are the dry season. So we're looking at data every month. So we're looking at how total water storage is changing, wet season, dry season, wet season, dry season, and we're seeing that trend. So, our jobs with some of these data are to figure out what the heck is going on. In that case, we were able to compile a lot of independent data and determine that we were looking at groundwater depletion. Okay, here's, well, this looks kind of crooked, but I just want to show you what's happening in Canada and a little bit in the United States. So now we're looking at a map of the trends. Okay, so this is the trend. Red is losing water, blue is gaining water for this 15-year lifetime of the GRACE mission. And so a lot of what we see is blue here in Canada, but we've got some of these very distinctive red spots. So what are we seeing? We're looking at glacial melt. And here's time series for western BC, and that's a lot of actually really dominated by the Alaskan glaciers melting, but also western British Columbia. And here's this spot up around Lake Athabasca where it's really losing a lot of water. There's been a pretty big drought up there. And that's probably indicative of the drought. It may reflect some of the water use in oil sands production. We haven't really looked at that in any detail. We had look off to the right, Baffin Island, of course, as we move towards Greenland in the upper right. Of course, that's melting away, so we see that decreasing trend. Here we are around Quebec City, and we see some increasing water storage, and then this big spot over here, which has been sort of wreaking havoc on the upper Missouri River Basin in the United States, and sort of an expression of the wetting and the increasing flooding that's happening in Calgary that actually swings over, underneath Saskatoon, includes Regina, and so, like someone said today, earlier discussion we had, doesn't mean that it's great because it's blue, right? And that's because we're really, especially when you have a deep blue spot like that, that's usually indicative of changing extreme, in this case, more flooding. So it's starting to show up in our data. Okay, so I'm going to show you this global map that I think for me and my group, I think of it as a real capstone achievement for the mission, and I'm very proud of all the work that my students have done on this through the years. This is a paper that we actually, for any of the students out there, papers don't just write themselves, and this one is one that we probably took about 7 or 8 years to write. Just because we kept getting new data, we'd reanalyze, we'd have some hypotheses, then new data would come in because we were working as the mission was collecting data. And so we kept reevaluating, and finally we waited till the end of the mission to submit the paper. So again, we're looking at the changing freshwater availability, or the trends, the regions that are gaining or losing water mass. Blue is gaining, red is losing. Okay, so what are we looking at here? We're seeing the ice sheets melting away, Greenland and Antarctica. I realize the print is a little small there. We're seeing glaciers melt away, so Alaska and down the southern tip of South America, and on the west coast of South America, so Colombia, Peru, and Patagonia. We're seeing some other climate change signals, which I'll get to in just a second. High latitudes and low latitudes getting wetter, and mid-latitudes getting drier. We're seeing a lot of interannual variations, so things like flooding in the Midwest that we just talked about, Orinoco and Amazon floods in South America, the Okavango floods in Africa. And so these are things that vary sort of with El Nino and the Pacific decadal oscillations, some of these climate oscillations. But they really do express some of the increase of the flooding and drought that we're seeing. And the next thing, really the last big feature of this map, is all of the groundwater depletion that's happening all over the world. So that's what, let me just go back, and so you can see those pop up. And we'll focus on these a little bit more. But some of the world's major aquifers, the Central Valley, the High Plains Aquifer, the Northwestern Sahara Aquifer System, in the Middle East, both the upper tier of the Middle East and the Arabian Peninsula are losing a lot of groundwater. Northwestern India, into Bangladesh, North China Plain in Beijing, Northwestern Australia, on and on. The Huarni Aquifer down in South America. These are the world's major aquifer systems. They provide the water for irrigation for some of the world's major food-producing regions. Okay, so not only are we losing water, our food security is at risk. I'll return to that point a little bit later. So there's a climate change component to this as well. And IPCC has been suggesting that the wet areas of the world will get wetter, that the dry areas of the world will get drier. This is a classic IPCC figure that's been around since the early days of the IPCC reports. And this one's showing the change in precipitation by the end of the 21st century. So the blues are increasing precipitation and the reds are decreasing precipitation. And so for a long time we wondered if that's what we were seeing in the GRACE data. And so we finally wrote a paper. There's some of the main plots that are showing all of the red areas in that map, the mid-latitudes getting drier. That's the upper part of the figure. And the wet areas getting wetter. With in the upper part, that's after we took out all those aquifers. So that's like the background, right? So this is the background drying that's happening. We think it's in response to climate change. So that's not necessarily great news. Okay, so we've got this map. Let's go back here. And the human fingerprint, I'll return to this at the end of the talk. Really what we're looking at is the human fingerprint, right, on the redistribution of fresh water around the globe. And so now we have to kind of adjust to that and think about how we might want to try to change it, or how we can respond to it, how we can do things like sustain groundwater so we can sustain food production. Okay, so groundwater. I've been talking a little bit about it, and I should have recognized that some people may not know what the heck I'm talking about. So groundwater is water that's stored under the ground in aquifers, and these blue units over here that are soils or rocks, and we have to pump it out. We have to drill wells. We have to pump it out. It's a primary water source for about 2 billion people. Provides about half of the water for irrigation globally. In many cases, it's non-renewable, especially in these deeper aquifer units that took hundreds of thousands of millions of years to fill up, and we're burning through it in some cases in a century. So I just want to show you, this is about as complex as my math is going to get. I had mentioned before that what GRACE shows us is the change in the total amount of water storage. And if we wanted to pull out, say, what the groundwater storage change was, we had to do some work, we had to get some extra data. So what I'm trying to show you here is that what GRACE is, this pointer isn't working great. So I'll do my best with my finger and other hand puppets, shadow puppets. Oh, I can almost do it. Nope. Anyway, okay, so what GRACE is showing us is the change. This is a river basin. Think of it as a big river basin, the Saskatchewan River Basin. GRACE is showing us the change in all that on a monthly basis. So that's what that equation is up on the top. The change in the storage, the total amount of storage is equal to the components, right? The total change is equal to the sum of the land storage, the surface water storage, the snow, the surface water, the soil moisture, and the groundwater. And so we could just rearrange that equation and solve for groundwater. Okay, so the significance of that is we're talking about doing remote sensing, right? Estimating groundwater storage changes, water that's underground from space. So that's cool because we can't see it, right? It's not on the ground. It's underground. So we use this, data from the scale in the sky to get at what the groundwater storage change is. So if we look at that bottom equation, GRACE, we get the delta S land from GRACE, and then we have to get the snow change, the soil moisture change, the surface water change from some other data set. It might be other satellites, it might be data on the ground, might be measurements, might be from computer models. We do, it's a mix. It depends on, if you're looking in a place like Iraq, we're not going to have access to much data. We have to use satellites and computer models. If we're working in the Saskatchewan River Basin, we probably have a tremendous amount of data available to us, so we can use a lot of observations. So conceptually, what we're trying to do, GRACE gives us this. If we want to estimate the change in groundwater storage, then we have to remove all that stuff that's above the water table. So get data for the snow, the surface water, the soil moisture, and subtract it. Okay? So just a little, since I used to work for NASA, I'm still get paid to do NASA commercials. So we hope to be able to do all of this from space. Actually, this is a research goal of mine, to try to do all of it from space. And so if we're going to solve this equation on the top, the change in groundwater storage, we need to, what data sources do we have to get the 4 terms on the right-hand side? We can get the total from the GRACE FollowOn, which just launched. We can get snow from a platform that's called the Airborne Snow Observatory, which flies over the Rockies and flies over the Sierras in California, does very high-resolution measurements of the snowpack, and we hope that it's going to be on a satellite someday. We can measure surface water storage changes with we have pretty dull names, I guess, for satellites. This one's called SWAT, Surface Water and Ocean Topography. It will measure the heights of rivers and lakes. It will launch in 2022. It will help us understand how water on the surface is changing. And SMAP, see, I told you, stands for Soil Moisture Active Passive, and measures the moisture in the upper few centimeters of the soil. So we hope to be able to do a lot of this from space moving forward. Okay, so anyway, this is just, I'm not going to dwell on this except to say we're going to go through the exercise. I'm just going to show you how it works when you take a place like, so California is shown over here in yellow, and then there's sort of a black outline of the big river basins, the Sacramento San Joaquin River Basin and the Tulare Lake Basin all together. That's most of the water in California, and the green part is the Central Valley. So that's this really productive aquifer system that provides tremendous amount of, provides about 90% of the produce that we consume in the United States, and a fair amount that we eat in Canada. There are some berries in some of our food today. Some of those may have easily come from the Central Valley. So all I really want to show you is the upper panel. That's the data from GRACE. We're looking at the total storage change. We want to subtract from that the data in the lower right corner, which is just the soil moisture, the surface water, the snow. So you subtract the lower right from the upper left, and you get an estimate of groundwater storage changes. And yeah, it's just a few, black line and a blue line and a red line, or a couple of red lines. But really what that is remote sensing of groundwater. That's estimating groundwater storage changes from space. So it's really cool. It's really been a huge technological advance, and we can do that all over the world now. Okay. So what that is showing us Well, let me skip to the next slide and show you. I'll put it in a longer-term context. So that's what we see over the Grace time period. Those red lines show the groundwater depletion during the last two phases of drought, 2006 to 2010, 2011 to 2015. But let me show it to you this way. Okay? This is the long-term picture of what's happening in the Central Valley in California. Stuff like this is happening actually all over the world in a lot of the aquifers that I showed you in that global trend map. So we're looking at 1962 to 2017. The lines there, the red is data from the United States Geological Survey, so observations. The blue is our Grace estimate of groundwater storage changes from 2002 to 2017. The colors in the background represent really the climate, what's happening. Is it a very wet period? That's the dark blue, right? That's when you see the lines go up. There's a lot of rain, the groundwater is being replenished. The dark brown is drought, okay? And that's when you see the lines, the groundwater lines going down, because we use more groundwater during drought because there's not enough water in our streams and not enough snow melt to fill our rivers. Okay? And the light colors are sort of in between variably wet to variably dry. So what do we see? Long-term decline, right? For actually this figure, there's a second half to that figure that goes back to 1930. So this has been going on since we started pumping groundwater in the Central Valley. So long-term trend of decreasing, and you see that we get a little bit of recovery in those blue rainy periods, but then a lot bigger drop. A little recovery, right, and a bigger drop. Okay. So that's our long-term trajectory in California and in many of the world's major aquifers. That won't change without legislation. We have new legislation in California I'll talk about a little bit later. I don't think it's really going to be sufficient to make a difference. There's other things that are happening here, which I'll show in some of the next slides. The average water table depth here in the green part there in the Central Valley, if you go right into the middle of the valley, the water table, the top of the groundwater surface, is down about 2,500 feet. It costs about $1 million, $1 million to 1.25, million to $1.25 million US dollars to drill a well that deep. So what that means is accessibility for the average person is really becoming quite limited. There's other things that are happening, stream flow, streams are being depleted, the quality of the water degrades as you go deeper and deeper into the aquifer. And we have this thing called subsidence. And so here's a picture of a famous picture from the U.S. Geological Survey. This is a hydrogeologist, his name is Joe Poland. He's standing next to a telephone pole in the middle of the Central Valley in 1977. Okay? And those signs that say 1925 and 1955, those show where the ground was in 1925 and 1955. Okay, that's called subsidence. So the ground sunk there about 50 feet in 50 years. Okay, so how does that happen? Groundwater subsidence is kind of like a tire deflating, right? If you let the air out of a tire flattens out. If you take the water out of some aquifers, right, that water pushes the matrix, the structure of the aquifer holds it together. You pull out, remove that water. In some aquifers, especially those that have clay minerals, you remove that support and the clay minerals are flat and they just flatten out. They stack up on top of each other and the ground sinks. Okay, so that's called subsidence. In California, it's happening at the fastest rates ever. And of course, anything that's on top of a subsiding aquifer, if it's dropping a foot per year, roads, bridges, there's all kinds of cracked roads and bridges in California. In fact, the U.S. Geological Survey page has those pictures and the GPS coordinates if you want to go see that stuff and keep track of it. So what are we looking at here on the left? We're looking at radar images of subsidence. Okay, we're looking at this. So this is the Bay Area here in California. So San Francisco is just off sort of in the center on the left-hand side and over here. And so we're looking in this box, that green box, that yellow box. And we're looking at two different time periods. This is sort of the first phase of the drought. And we're looking at subsidence rates of up to about a foot per year in the middle. Okay. But in the second phase of the drought, which was much more severe, we're looking at rates that are on the order of, well, the worst are 14 to 16, so a foot and a half per year. Okay, and this even got worse. In 2015, 2016, there were right in the center of that bowl, there were subsidence rates of 2 meters, sometimes 3 meters per year. So it's pretty crazy. We can even do a better job. So this is from satellite, but if you put the radar on a plane, we can get very high resolution maps of the subsidence. In fact, now NASA Jet Propulsion Laboratory is doing that for the state of California, in part to figure out, we can see the individual wells, right? So we can see who's over pumping. And I mentioned we have this groundwater legislation. So at some point it's going to become illegal to over pump, and we'll be able to see some of the subsidence if people are illegally pumping. Okay, so there's Joe, excuse me, in 1977, and we photoshopped him to really reflect the full scope of the full depth of the subsidence. So I went from here to here. Okay, that's happening. I was at Phoenix. I gave a talk in Phoenix, and we were really looking at the whole. So the focus of the meeting was the southern tier of the United States, and so I wanted to show the occurrence of subsidence. It's not just, you know, that spot where Joe Poland was standing, but it's happening in all these different places in the United States. So it's not like the whole aquifer, you know, is subsiding, but there are pockets of subsidence in all of these regions. Okay, I want to talk a little bit about the Colorado River Basin. You know, there's a policy side to this, which I think is really important. So Colorado River Basin, you know, there's this sort of allocations were done in the 20s, and there's sort of this loose system of agreements and treaties. I forgot what it's called, like the law of the basin or something like that. But there are these fixed agreements for how the Colorado River Basin water should be allocated. And they were just renegotiated. It's called a drought contingency plan. So some of you may know about it. That's because the water in Lake Mead, the biggest reservoir in the United States, keeps dropping and dropping and dropping and dropping. And pretty soon it's going to go below the level of the pumps, so it'll be useless. Okay? If we get to that point, that means there'll be like no electricity for Southern California, where like 20 million people live. You know, no water. So this is something that all the basin states, which are shown here on the map, in Mexico want to avoid. So they renegotiated. And they came to an agreement. But what they didn't agree on or even really talk about was groundwater. So it's really about surface water. And this is a big problem. Groundwater often gets left out, maybe this way in Canada. Remember, I'm new here. I just moved here. I'm the new guy. I just moved here in July. So, and I'm talking about you know, a lot of global stuff today. I don't know how we manage our groundwater in Saskatchewan, but in the United States and a lot of places in the world, it's either not managed, loosely managed, it's managed separately from surface water, and in many places around the world it's just disappearing. That's why we have all those red spots on that map. So what happened in the Colorado River Basin, so first let me show you what we found. So we wanted to know what were surface water losses, meaning from the big, huge reservoirs, Lake Powell, Lake Mead, which are these iconic reservoirs in the United States. So what were they doing compared to the groundwater? Okay, so we did one of these studies that I described for California in this time period here, 2004 to 2014, using the GRACE data. So the upper panel showing the change in all of the water together. We can't tell from that upper panel what's surface water, what's groundwater. It's just there's a trend, there's wet season, dry season, there's a downward trend, something's happening. How much is being lost from the reservoir? How much is being lost from the groundwater? That's the bottom right panel. The red, that's the losses in, I can't deal with this pointer, so I'm going to go mobile here, okay? So the red, this is Lake Powell and Lake Mead. This is our estimate of groundwater. So we're paying a lot of attention to the river. You know, looks okay relative to the groundwater, which we don't pay attention to, and it's disappearing at a rate of 6 or 7 to 1. Okay? So that is threatening the water security of the western United States. People don't want to talk about it. Even with this drought contingency plan, they still didn't really want to talk about it. Basically, they said, okay, Arizona is going to lose a lot of water because it's sort of the last one on board in the Colorado River Basin Pact. So they stand to lose. They're going to be the first people to lose water if the drought contingency plan kicks in. And the farmers in Arizona will be the first ones to lose it. Okay? So the solution is, farmers just use groundwater. Okay, that's the solution. And it's more or less unmanaged. And that's what's going to continue happening. Okay, so that's just an example of how even today, groundwater is still not included in major transboundary policy within countries and between countries. Okay, I mentioned the United States before. This is the lower half. I showed you that Canada map. You know, the issues that we have in the U.S. are the upper half is getting wetter and the lower half is getting drier. Okay, and those two big red spots on the bottom are our two big food-producing regions. The Central Valley here in California and the Ogallala or the High Plains Aquifer. So we grow a lot of produce, a lot of dairy over here. Hello, people over there. Grow a lot of dairy over here. We grow a lot of grains over here. Okay. This region expects to run, the southern part of the High Plains Aquifer expects to run out of water in 3 decades. Okay. They're making a conscious decision to use the water. California, if we don't do anything, we'll probably run out of groundwater in about 60 years. But we do have this legislation called the Sustainable Groundwater Management Act, which again, I'll get to that a little bit later. It's going to take about 25 years to implement. So my fear is that there won't be any more groundwater to manage by the time it gets implemented. So let's go global. We'll start to go global. So now we're looking at an animation for India, northwestern India. Oh, I showed you the Middle East one already. Sorry, it's a rerun. So the top is northwestern India. Northwestern India, that's probably the greatest rate, the highest rate of groundwater depletion that's happening in the world. And right, it's on the border with Pakistan and NASA. So most of my work through the years was funded by NASA, and the head of Earth Science, when that paper came out, that was our first sort of paper that really pointed to groundwater depletion. And he was afraid, you know, that we were going to stir up some conflict between India and Pakistan, which I don't think ever happened, never heard of it. Okay, so I showed you this map before, and I just want to highlight the groundwater part of it. So I showed you before that these are all the aquifers that are being depleted. And so I had a student who did some work on groundwater stress and water stress. You know, we do these stress indices. And so she took these data. This is a picture that just maps, right? It maps that, those aquifers to this template. It shows that aquifer specifically. But in this paper, we were able to say conclusively that over half of the world's major aquifers, there's 34, over half of them, like 20, are being rapidly depleted. They're past sustainability tipping points, and that's because we're using it. I mean, we need to grow food, right? We had an awesome dinner, but we need to keep growing it. And so we need to start thinking about how to use the water more sustainably, how to manage surface water and groundwater together. So this is our future, because we need to sustain this for the long term. Those are just some of the time series for those aquifers. You can see that there's a downward trend in all of those. All right, what are some implications and emerging policy needs? You know, again, I'm no expert here. I just look at these things and think about some issues, and I want to share them with you. And I hope that they trigger some ideas that perhaps we could work on together moving forward. Because, you know, there's an urgency around, you know, I didn't have enough coffee today. I have a little bit of a sore throat. Usually I'd be, you know, I walked around the stage a little bit, but usually I'd be jumping around and really, you know, excited. But there's an urgency here, and there's an urgency about climate change. You know, we need to act, okay? And so let's just, these are just some ruminations I've been having over the last few years. So here's that map, just a sort of different color scale, but that's the map. And so I said this earlier, the human fingerprint on the freshwater landscape. through climate change, right, ice melting, the changing extremes, and water management, groundwater depletion, is a dominant force. It's dramatically, I mean, that's dramatic change, right? So when we launched the GRACE mission, there was no expectation that we were going to see anything like this. And this is what we got. It's a dominant force that's dramatically changing patterns of water availability. That change is happening far more rapidly than most people realize. Most people here, except for the ones that I talked to earlier today, probably had no idea. Okay? So we have to prepare, it's a policy seminar. Let's think about some of the policy needs and innovations that we need to cope with this. There are some implications for food-producing regions. Most are in a state of what I call chronic water scarcity. It's not drought, right? We're into deficit spending. We're using that groundwater, and it's disappearing. That's why we have all those red spots, right? That's why over half of the world's major aquifers are being depleted. We use more than we have. The water's insecure, right? We use more than is available to us. So we got to work that out. And there are a lot of solutions for metropolitan regions, like sewage recycling, desalination, we were talking today, conservation. We did a great job in LA during the drought, but less so for agriculture because it takes a lot of water to grow our food. So we have to figure out how to do it more efficiently. And until we figure out something brilliant, we have to be taking the smaller steps of being as efficient as we can with our water, to drip irrigation, deep drip irrigation. We were talking about Israel earlier today. There's so much greenhouse agriculture that's going on there. Changes in pricing, changes in what crops are grown where. These are things that we have to start thinking about. Okay, so I don't know if you thought about this, but if you think about that map of the US that I showed you, the upper half is getting wetter, the lower half is getting drier. We grow our food in those big red spots that are running out of water. Okay? And we can say this about really any of the world's major aquifers and food-producing regions. If we want to keep growing food in those regions, they're running out of water. So, we have to conserve the heck out of the water. But at some point, if we want to keep growing there, we're going to have to move water there. Okay? Maybe we'll move the food to where the water is. Problem is that it's really sunny in those dry spots. So these are things that we're going to have to work out. I'm not advocating, I'm just saying this is just the math. They're running out of water. Okay, so either we're going to move water to where the food is grown, move the ag to where the water is, or somewhere in between. So we've got some thinking to do. Oops. Oh yeah. So there's that U.S. map. So you can see there the upper half is wetter, the lower half is drier. So we may need to move water if we want to keep growing in California and the Ogallala aquifer. So really, these food problems, in California, we always thought of it as a California problem. But it's really not. It's really a national problem. Maybe it's an international problem. We're like killing ourselves during the drought, trying to save water to grow food for the nation. Okay? So we have to be thinking about that. Right? And if we all got along as a global society, then we could grow food, right, in different places and share the water and share the food, but we don't because we want to be internally secure. And so that creates a lot of issues. So, implications for human security. There are distinct classes of the haves and have-nots. If you're in a wet area, you're a have. If you're in a dry area, you're in a have-not. You're a have-not. If you live over, in the Central Valley, and you can't afford to spend $1 million on a well, which most of us can't, then you're a have-not. And so those distinctions are growing. Migration, we're doing managed retreat already in the United States. So migration, managed retreat, and managed resettlement are already happening. Okay, so there are some policy issues we have to think about here. Unmanaged migration, climate refugees will increase. I'm pretty sure violent conflict is going to increase. A lot of those spots that I showed you on the map were transboundary. Issues surrounding repeated resettlement and in fire and flood-prone areas. Really, all I'm getting at here is how many times we're going to let people move back into these fire-prone valleys in California, or they're just going to burn, right, the next year. Or same thing now with people that live in the floodplain. We've got the increasing frequency of flooding here in Canada. we can't go on like this. So how will migration immigration policy be framed to accommodate and govern displaced populations? So just, as these people are on the move, how are we going to take care of them? How are we going to govern them, right, with these sorts of disruptions? And just sort of throw this in there. Another thing we really have to think about, especially with the repeated frequency, increasing frequency of the extremes, flood, drought, flood, another drought, right? We don't have time, resilience to recover from that takes money. And so, not only do we have to recover as people, but it takes money. And, do we have the sustainable, are we thinking about the sustainable disaster relief and insurance flooding? Is that itself sustainable? For groundwater management, I've kind of talked about that, but we really need to recognize and accept that we use, especially in these food-producing areas, really our water is insecure. We use way more than we have available to us. Again, that's where we're sort of in deficit spending. We have these red sort of negative balances on that grace map. So we really need to be thinking about managing surface water and groundwater together. That's why I said it's foundational, right? We've never done it. Again, I don't know what's happening here in Canada, but in the United States, we have never done it. It's manage the surface water and free-for-all on the groundwater, okay? So that's crazy. And if we had to do it all over again today, we'd do it this way. But, there's legacy policy, there's legacy water rights that are very, very complicated. I mentioned this before. We need to recognize that groundwater is really a critical element of national and international water supplies. I mean, it's essential to the survival of the Western United States, but it doesn't even get discussed in the basin policy. So I mentioned this already. Just, these are some test cases. So I mentioned the Colorado River Basin Drought Contingency Plan, and I said, but, the farmers are just going to, switch to groundwater, okay? Well, there actually is a Groundwater Management Act in Arizona. It's now going to be put to the test, okay? So is it going to have any teeth or not? And if it doesn't have any teeth, then we're going to have some really big issues in the southern part of Arizona. And I mentioned California's Sustainable Groundwater Management Act, same thing, okay? I think sustainability is a misnomer. Okay? Again, we're talking about in California, maybe in Arizona, maybe a lot of these aquifers, certainly in the southern part of the High Plains aquifer over there in Kansas, Nebraska, Kansas, Oklahoma, Texas. We're talking about managed depletion there. Really, we're talking about managed depletion in California, probably in Arizona, but no one says that. They say management, they say sustainability, but that's not what we're after because we can't grow food. We need the groundwater to grow the food. So we've got some issues. I'm scaring you, I can tell. I see all the way to the back of the room. All right, what are we going to do about it? Okay, so this is the signal that we're almost done because I don't really know, okay? But it is why I moved to Saskatoon, right? The opportunity to think about what we can do, right? To get out of the government situation where I couldn't really act on it, right? To be a nice water institute. Canada's investing a lot of money in water. It's an opportunity to work with you folks to think about, I'm just glad I have the opportunity to start to think about what we can do with you. So I don't have any answers. I don't want to come in with answers, but I want to work with you on the policy side. What can we do? What are the policy needs? What is screaming out to you? Before I just thought, I was making you feel real bad, and I just want to put a nail in the coffin right here. So this is the urgency. This is sort of motivates the urgency, right, that we need to get our acts together and start working on this together. So the Canadian Climate Change Assessment came out like last week or 2 weeks ago. And if you haven't seen it, it's pretty darn bad. So precipitation is projected to increase for most of Canada. And that sounds great. except that a lot of it will be delivered as floods, and a lot of it will be delivered as liquid precipitation rather than snow in the mountains. And so that becomes a problem if you're trying to capture it in reservoirs. So that may not be all good. The seasonal availability of fresh water is changing with an increased risk of supply shortages. In the summer, this has to do with earlier snow melt, right, and too much water running off too soon. And then warmer summers, so more evaporation, so less water availability in the summer. A warmer climate will intensify some weather extremes in the future, including flooding, drought, and wildfire risk. And I have to say, I wasn't thrilled to move to Saskatoon, and the first few weekends we were here had all that smoke coming across from BC after leaving California and driving through fires. So it's fires up the west coast. Get into Oregon, it's beautiful. Get into BC, it's beautiful. Get outside. So we drove up the coast and then over across to Saskatoon. And as soon as we left BC, the fire started and the smoke. First few weekends we were here was really, really smoky. So I mean, this is our future. Canada will experience more extreme heat, less extreme cold, longer growing seasons, shorter snow and ice cover seasons, earlier spring peak stream flow. Well, that's a nasty list. Thinning glaciers, thawing permafrost. Maybe the less extreme cold is good. Longer growing season is, could be great, but it means more stress on water resources. So I have to be really, really careful about that. Okay, so some perspective. There's an urgent need for us to work together on thinking about regional and global. And it doesn't have to be regional. I think we have an opportunity here to take global leadership and understand what role universities can play in, beyond Canada. What can we do globally for water and climate policy innovations? I think that we really, we had some conversation about this earlier today. We academics, in the old days, it was cool to be in the ivory tower and do this awesome research that no one but you and your supervisor understood. But those days, right, for the old people, wasn't that cool? We felt so smart. But now, those days are gone, right? And so we really need to engage with policymakers, planners, stakeholders, and the public to discuss these adaptation strategies and discuss some of the policy needs. People like me need to bring the science, these graphs and other things that we're working on, bring them to the table, right? So make sure that our decision makers see the best available information. And we also need to integrate across disciplines, right? So it's no longer just hydrology. For me, I have to engage with social scientists. We were talking about, a lot of the change that needs to be made is behavioral change. We have to really get inside people's heads and understand, how we can help them. If you're in California and you've been conserving water for, 3 years, you have to understand now that's a way of life, and it's not time to go back to watering the grass and, right, wasting water the first time it rains, which is exactly what happens, right? So you conserve. A couple of days rain, like, oh, wow, drought's over, and all the savings go out the window. So that's a social behavioral thing. So we need to integrate across disciplines and, of course, across institutions. I'll certainly look forward to working with everyone here on this. A lot of what I just talked about is in a magazine that's available online. And the issue, so the whole issue is about water. This is from the Pew Charitable Trust. So there's the website down there, trend.pewtrust.org. The issue is called The Future of Water. In my article, it's called A Map of the Future of Water. They did a really nice layout, and I used some of those pictures today. So that's a resource for you. Oh, here's the take-home. I love it when other people tell me what the take-home is. So let me reread it and see if it's the take-home that I want you to have. The world's wet regions are getting wetter as dry regions are getting drier, much more quickly than previously thought. So true. Changes that threaten the availability of fresh water and create new risks to people's health, the food supply, and the environment. Yeah, I mean, I think that's the bad news right there. Succinctly. So for more information, you can go to that Trend site, get that paper. My personal website is just my name, and I always say the same thing at the end of a talk. I would, this trip will be a colossal success if I get one new Twitter follower. That's all I ask. So that's it. Thank you very much.
Thank you so much, Jay, it was a really informative talk with lots of things to think and worry about now.
You're welcome.
Yeah, so we do have time for questions. Apparently I get to ask the first one, but while I ask the question, there are a couple of microphones in the center of the room, so if you do have questions, then you can just work your way to that microphone as people are coming up. So I just wanted to say, first off, thank you so much for really emphasizing the need to manage the surface water with the groundwater at the same time. And I was wondering, thinking locally here in Saskatchewan, one of our major issues, a fairly hot topic these days, is drainage, and how people are draining surface waters in order to reduce flooding, to increase agricultural land and so forth. And I was wondering if you saw some validity, if there's any options for mitigation of groundwater depletion in terms of reintroducing some of these surface waters back into the landscape, if there was an opportunity in that case to help our water issues in Saskatchewan.
Oh, sure. So are you saying, is this on? Are you saying that, are you asking about the opportunity to take that drained water and use that to replenish aquifers?
Well, if we didn't drain it in the first place,
Yeah.
whether that would be aiding in our aquifer recharge.
Right.
But if we, start introducing things like restored wetlands or, putting
sure.
them back
No.
in, if that would be a feasible management
Right.
option.
So, absolutely. And in the NGO world, the buzzword is that's a nature-based solution.
Yes.
Which really means, we probably shouldn't have changed it in the first place, and it'd be great to go backwards and restore.
Yeah,
right,
I think
what we used to do. So absolutely. And we may be thinking about doing some of that. Of course, there's the need to drain the farmland so it can be productive, but it can be a balance.
Yeah, I guess I was also curious about the relative impacts of the climate change versus how we are managing our surface water and how big of a difference that would make, and if we could calculate that, if we could figure out the relative effects.
I mean, it sounds like more research is necessary. Yeah.
How are we ever going to do that?
Yeah. I mean, I think we have to be thinking about, we need to start to understand baseline water budgets in ways that we haven't done before. And part of that is assessing like how much groundwater is there. Like that's the part that always gets left out. Mm-hmm. So if we could do that, that becomes a nice baseline. Then we can think about, sort of the water, the basics of water security. How much do we have? How much do we need?
Yep.
And how are those changing over time? And so we need to start to collect those data.
Thank you. People haven't been moving up to the microphones.
I know why that happened. It's because they all went to the bar before the talk started, and here we are.
Oh, there we are.
I'm a little shorter than the microphone. My name is Kristen Bruce. I'm here from the city of Saskatoon, and I'm leading a project to create a climate change adaptation strategy for the city. And I was wondering how best...
Where do you live?
Right in Saskatoon.
Nice. Okay, I'll come and see you.
Great. That's my question. I'm wondering how best can municipal government engage with academics? How do we bring people to the table?
Call me. Just 1-800-CALL-J, and we'll be there. At my institute, I don't think there was a lot of that before. And I think the focus was really on hiring faculty and getting a lot of instrumentation out across wide, swaths of Canada, Saskatchewan River Basin, Yukon Basin. But I'm much more, like I used to be on, when I was in California, I was on the State Water Board, so appointed by the governor. So we'll talk. I'll be your connection, okay? Here, come, I'll give you a card right now. Right. I always do this. I always try to give you someone else's card. That's not the card I want to give you. I want to give you my card. There you go. All right. Thanks. Thank you.
Coming up.
Steve Vischer from
Hey, Steve.
Hello, Jay, from the Global Institute of Water Security. I think one of the things...
No, you're from the food security.
Food security, sorry.
Yeah, I'm
Yes,
from the Global Institute for Water Security. You're from the Global Institute for
Food Security, indeed. But there's and one of the comments I would make is that I'd like to pay tribute to Jay. He mentioned that he'd come here for a reason. He wanted to do things, and one of the things he's already starting to do in and around the campus in Saskatchewan is to help connect people. And one of the people he's been reaching out to is the Global Institute for Food Security. But I'm interested, Jay, in beyond that and that sort of bilateral arrangement, about how you see this area and this province can work together on some of these huge challenges, because I sense that we have some terrific expertise present here, perhaps working to a degree in silos historically, but with an opportunity driven by the force of the data that you presented, to actually say we need to do something, in a policy sense with the government, provincial and federal. I just wonder if you've got any more thoughts from your early time here, less than a year, as to what you see the bigger opportunities are.
So thanks so much, Stephen. Thank you for coming down. I really appreciate it. So I think there's great opportunities. I think the issues are that we have to, as a new person, I'm sorry, I can't see you in the lights. As a new person, I need to personally, you may have these relationships, but I don't. So we can work together, but we have to establish relationships with the interested parties, the right ministries, the right departments, build that trust, find out where the mutual interest is, and go from there. But I think the future is really bright. And so, there's two aspects to the water security stuff, and I sort of said it when I said metropolitan areas might be a little bit more easy to deal with. I think they're sustainable, but food, right, we use 80% of the water that we withdraw, we use it to grow food. And so if we want to manage the water crisis and water security, we have to tackle food and water together. And so part of it is just getting that message across, Steve, and letting people know that we're really willing to come down and meet folks here, and the JSGS can help us do that. I think the future is quite bright. I think one of the things that I would like us to do, and you asked about further thoughts, it's the part about working directly with the stakeholders, right, and the policymakers, right, understand what the stakeholders, what the agencies, what are the questions they're really grappling with, but also we can share some of the information that we have, so we find that middle ground. Rather than we have to avoid coming here and saying, look at how awesome we are. You should do this. We can't, we're past doing that.
We've got time for one more question.
This is a science question. Obviously, climate is going to affect an aquifer, but does a depleted aquifer affect the local climate?
Yes, it does, in a couple of different ways. So, and it depends on the structure of the aquifer. So if it's close to the surface and intersects with the stream, then those don't really tend to be depleted, but maybe with climate change, some of them will. And so that's going to affect stream flow, and that's going to affect feedbacks to the ecosystems and feedbacks to climate. But really the bigger way is through irrigation, right? And so we take that, there's analogies with the carbon cycle. But, we take that fossil water out of the ground, we put it on the surface, we water plants, we get more evaporation. So we're fundamentally changing regional climate. So we did a study that looked at what happens to the climate around the Central Valley. And what we found was that irrigation and the extra evaporation that's generated by that irrigation, that water vapor travels to the southwestern U.S. monsoon system and strengthens the monsoon, because water vapor is a greenhouse gas. So the water vapor, right, flows with the circulation into the monsoon region, which is very active, so it gets caught up in the circulation, strengthens it, right? So you just get much more variability there. And we're now in the process of kind of looking like aquifer by aquifer, what are the sort of regional impacts, and then what are the global impacts.
Okay, so with that, I guess that's it for questions, but you can always ask questions to Dr. Famglietti after the formal portion of the evening. So if you want to join me in thanking him yet again for a really interesting talk.
Yeah, thank you.
Wow. Dr. Famiglietti's presentation demonstrates the need for responsive public policy to our changing climate and environment. Dr. Famglietti, on behalf of the Johnson Shoyama Graduate School of Public Policy and all of us here, thank you for your presentation and joining us here tonight.